guys, so we're continuing on with our quantum mechanics in 3 dimensions. We had just finished talking about the angular equations in part 2 of this series of videos. So we're gonna zoom in on our radial equation, which, remember, when we separated our variables, it's this thing in the first set of brackets that we set equal to L times the quantity L plus 1. Okay, so that's where we're starting out with this equation. So what we're going to do, we are going to go ahead and substitute into that equation. We're going to substitute a function that we'll call a function of r, u of r, for anything that is our variable r, so our radial variable, times our radial function r as a function of r. That's a lot of r's. Okay, so when we do that substitution, what we're going to see is that our information in the brackets starts to look like this. So we've got v, we've got h bar, 2m, okay, so this is our Schrodinger wave equation, right? But that is just coming from this information in the brackets being set equal to L times L plus 1. All right, so that Schrodinger wave equation, then, we are going to do a little work. But first, I want to label this thing that's in this set of brackets. This is what we might call our effective potential energy. So we'll give it a little EFF as our effective potential energy there on the bottom, right? Okay, otherwise it's pretty identical to the one-dimensional Schrodinger equation, right? We have an h bar squared over 2m times the second derivative. We have this thing that we're going to relabel as our effective potential energy times our original function, and we have our energy times our original function. So here, the u as a function of r is standing in for what we called psi in our one-dimensional Schrodinger equation. So since we've already seen that, we already know how to solve it. So in our effective potential energy, or our effective potential, there is something that we're going to call the centrifugal form. So there is this extra little something that's our h bar squared over 2m. We've got L times the quantity L plus 1, and that's over r squared, right? So there's that extra little term that we would call the centrifugal term or the centrifugal form. For the same way that we've done it before, we would normalize this equation. So our normalization looks like, again, because r goes from 0 to infinity, we would normalize this function so that over whatever space it exists, our normalization equals 1. So really, to go any further with the solution for this, we need a potential energy, a specific potential, to go further with our solution for the radial equation. So luckily, we do have one of those that we can look at. We can look at example 4.1, right? So example 4.1, I'll get to it in my book, says, consider the infinite spherical well. right? So an infinite spherical well, oops, rather than our infinite well in one dimension, looks kind of similar, right? So we're going to say that there's a potential of 0 within the well, so R less than A, and there's a potential of infinity outside the well for R greater than A. Looking in 3 dimensions, we're kind of setting this distance A, where inside the sphere our potential is 0, and outside the sphere the potential is infinite. So just like our one-dimensional infinite well, or infinite square well in that case, we can say that our wave function doesn't exist out here where the potential is infinite, right? So our wave function only exists within that well. So outside, our wave function is 0. Inside, we would do the radial equation. Let's get more paper. So inside our well, our radial equation says something like this. And this is just taking that equation that we have on the other page and substituting in and moving some things around. Okay, so what have we done there? Let's define what this K is. So this K we've used before. It's our square root of 2me over h bar. So K squared is just 2me over h bar squared. So what we've done there is we've taken this equation. Inside the well, this potential energy is just 0. So we have the centrifugal form for the effective potential energy. We've multiplied some things over and moved them around so that we have this differential equation. Right? So if we have this differential equation, what we want to do is we want to solve this differential equation and then subject it to the boundary condition that our wave function has to be continuous. So our wave function at that point A has to go to 0. Right? Okay, so we can do that, right? You can do different cases. So remember, L is going to be an integer. So we can start at 0. We can start at L equals 0. And that one's pretty easy because our differential equation, this first part disappears. So that case for L equals 0 tells us that the solution looks like, or the differential equation looks like this, which means the solution to that differential equation looks like a sine and a cosine. Right, so that would be a solution to that differential equation. So if we remember that the actual radial function that we wanted to start out with is this function of r, this u of r divided by our r, our variable r. And we remember that our cosine of kr function divided by r is gonna head towards infinity as r heads towards 0. That's not a well-behaved function. So that's gonna lead us to saying that this b is gonna be 0. Okay, so just knowing that this is not well behaved, when we get to our actual radial function, our B in front there goes to 0. Okay, so then the boundary condition, remember our boundary condition is that when we evaluate this at A, we should get 0. That requires that that equals 0. So really either our capital A, our normalization constant in front there, equals 0, which would make this kind of a boring, trivial answer, or it tells us something about this K and tells us something about allowed energies. So we're going to go with a more interesting solution that Ka is going to be an integer multiple of pi, so some integer n. So then that's going to lead us to talking about allowed energies in this sphere that we'll name n0. So n for this constant, or this integer, and 0 for the fact that we are still in that case of L equals 0. So our allowed energies, and this is again going back to our definition of K and this boundary condition. Our allowed energies are n squared pi squared h bar squared over 2m a squared. So the size of our spherical well, remember A is that radial size of our spherical well, matters. And this is for integer multiples of n. Great. Okay, so then the same as what we did for the one-dimensional square well, we would have to normalize this function. So if we normalize this function, that will give us that capital A that is our normalization constant. We're going to normalize this function, u of r, and we are going to find, same as with our infinite square well, that our normalization constant looks like the square root of 2 over a. So once we do that, we have a function that we'll denote with an n and an o again, because we're in this case where L equals 0. And that function looks like the square root of 2 over our lowercase a times sine, and we've decided K looks like n pi over a times r in that sine function. So the radial wave equation has n minus 1 nodes, or you could say n lobes. And the general solution for an arbitrary L is a little different. So we'll write that one down so we have it in our back pocket. General solution for an arbitrary L is going to be this UR A times R, and we'll throw another letter in here, J, that will give a subscript L2. That should be a KR in there, plus B times R will give us an N with a subscript L and a KR in there as well. So in this case, that J and that N are Bessel functions. So J with the subscript L and the argument, whatever the argument is, in this case it's KR, but we're going to be generic and say X is a spherical Bessel function. Now it's a spherical Bessel function of order L. And NL with the argument X is going to be a spherical Newman function. I guess I got to capitalize his name as well. Okay, so let me define those functions for you. To define these functions, we need to go to kind of a long equation. So J with the subscript L, remember this is our Bessel function, and the argument X would be defined as minus X to the L power, 1 over X d dx to the L power, acting on sine X over X. Now remembering that the thing that we have in this argument is K times R, right? Okay, and then our Newman function, our spherical Newman function, that is n with the subscript L, X, is defined as negative X, that quantity to the L power, 1 over X d dx, L times, so to the L power, cosine of X over X, right? And remembering the X, our argument is this KR. Okay, so for example, and I'm just going to show you what's in your book. For example, where L equals 0, we just had sine X over X. Where L equals 0, we had minus cosine X over X. Where it equals 1, gets much more complicated, 2 even more complicated, right? And so on. So the first few spherical and Bessel and Newman functions are listed on a table in your textbook for quick and easy reference. But if you need it to just figure them out on your own, there is a very logical way to figure them out. So the Bessel functions are finite at the origin, but the Newman functions blow up at the origin. So for all of these, we're going to see that our normalization condition for the Newman functions goes to 0. So our radial function simply is a function of r, is whatever our normalization constant is, times our Bessel functions, where the argument of those Bessel functions are kr. Right? So there remains a boundary condition that our wave function needs to be continuous. And so our wave function, when evaluated at the boundary, needs to go to 0. So we need to choose a k so that the Bessel function, when evaluated at that point, goes to 0, right? So Ka is a 0 of the nth order of spherical Bessel functions. Since the Bessel functions are oscillatory, and you can look on Wolfram alpha and see a few of them shown that way, you're going to see that they have an infinite number of zeros, but they're not located at nice easy points like multiples of pi, and they have to be computed numerically. So the boundary condition requires that these k's, we'll call it a beta L, where beta L with that n L is the nth 0 of the nth spherical Bessel function. Right, so you're finding those spherical Bessel functions, and the zeros, the nodes for those, right? So that makes your allowed energies, the nth allowed energy for the Lth spherical Bessel function, so L equals 1 or 2 or whatever it equals, is going to be given by h bar squared over 2ma squared, and you're going to find these locations of those zeros that'll correspond with the nth allowed energy. All right, so here we're going to introduce the principal quantum number n, which simply orders the allowed energies from the ground state. Right? Okay, so I will introduce that quantum number. Ooh. So this orders the allowed energies, and the ground state energy is just at n equals 1. Okay. So our solution to this whole set of example problems is going to give us a wave function that is going to be a function of all these quantum numbers, the principal quantum number n, the magnetic and the angular quantum numbers m and l. And this will be a function of our 3 dimensions, since we're in spherical. We are going to have a normalization constant that is going to depend on both our principal quantum number and that that L quantum number. We are going to have our Bessel function, so J, that is based on these variables, including where the 0 position is. We are going to have our angular function that we already solved for, that is based on our quantum numbers m and l, and the arguments for our angular function are theta and phi. So the constant a with the subscript n and l is going to be determined by normalization, and this wave function is going to have n-1 radial nodes. Okay, so that looks like a good place to stop. We're going to start with the next section on the hydrogen atom in the next recording.